In this episode, you will learn everything you need to know about virtual threads, one of the major new features of the JDK 21 to avoid blocking a platform thread. This is exactly the role of a virtual thread. And instead of blocking the platform thread, it unmounts itself. You will learn why they have been added to the JDK, how you can create them, how you can use them, what performances you may expect from them, and how they are working under the hood. Let us start from the beginning. Why virtual threads have been added to the JDK? The effort to add them was huge. It took years. The pull request on the JDK was massive, so there must be a good reason. Virtual threads are there to solve a problem that has to do with asynchronous programming. So let us start from there. Suppose you have to query a remote database for a user object. You have the name of the user and you need to fetch the full user object from your database. You are probably going to write this kind of code. First, you need to create a request with all the information needed, probably in the form of a JSON object, and then you need to launch this request on the network. After a while, you get a response, probably in the form of another JSON object, and then you unmarshal this object to recreate your user object. This is the kind of code you end up with. Simple to write, simple to read, simple to debug, simple to test, and simple to maintain. How busy could your CPU be when it is performing this request? Well, the first step is pretty simple. It's just in-memory computations, so you can assume that it will run in the order of several tens of nanoseconds. The second step is a request over the network. This one takes much longer, probably in the order of the hundred of milliseconds. And your CPU is not doing anything during this time. It's just there, waiting for the response to come from the server. And then the third and last step is also in-memory computation, the unmarshalling of a JSON object. So that's another tens of nanoseconds. On the overall, this code executes in about 100 milliseconds. So to compute how busy your CPU is, you just need to divide the time it takes to prepare the request and unmarshal the JSON response, that is several tens of nanoseconds, and the time your CPU is waiting for a response from the server. And that gives you 0.0001%. That's the order of magnitude. In a nutshell, your CPU is idle during this request. The first solution you may be thinking about is to launch more than one request in parallel. And the classical model is to have one request per thread and launch as many threads as you can. This has been working for years ago. The real question is, can you keep your CPU busy 100% of the time with such an approach? So let us do the math. How many threads would you need to keep your CPU busy 100% of the time? Well, the math is actually pretty simple. With 10 threads, you have a CPU usage of 0.001%. 100 threads will give you 0.01%. With 1,000 threads, you can expect 0.1% CPU usage, and with 10,000 threads, 1%. To have a CPU busy 100% of the time, you actually need 1,000,000 threads with this model. It turns out that a thread in Java is actually a thin wrapper on an operating system thread, sometimes called a kernel thread or a platform thread. And these threads consume quite some resources. Typically, creating a thread takes 2 megabytes of memory upfront, So creating 1 million of them would require 2 terabytes of memory, which is a lot. But there's worse. Creating a kernel thread also takes time, in the order of the millisecond. So creating 1 million of them would actually require 1,000 seconds, which is a little more than 15 minutes. Actually, if you try to create threads in a loop, depending on your operating system, you'll probably hit a limit long before that, at about a few thousand threads. So if you use this approach, you will quickly reach that limit, and your CPU usage will still be very low, in the order of 1%. So unfortunately, the solution that consists in creating one thread for each request is not a viable solution to increase your number of requests per second. This has been known for years, and this is why other approaches have been explored with success. If you take a step back and examine the initial problem carefully, you can see that you have actually 2 solutions to improve this situation. On the one hand, you want to increase the number of requests per second. To achieve that, you need to launch your requests in parallel. Launching one request per kernel thread does not lead to viable solutions because kernel threads are way too expensive. So at this point, you have indeed 2 solutions. Either you create a new type of threads that are less expensive than the current kernel or platform threads, or you launch more than one request per platform thread. Launching several requests per thread means that you cannot write your code using the imperative approach anymore. What you need to do is to split this code into small atomic operations. Each operation gets inputs, is doing one thing, and produces a result. So what you need to do is to write all these operations as lambdas, and then you need to wire them together using an asynchronous framework. In a nutshell, the job of this framework is to call your lambdas with the right inputs, to get the outputs, and to transmit these outputs as inputs to the next lambda you defined. What you are creating are pipelines of operations that process your data and that are executed by the framework you are using. The responsibility of this framework is to correctly execute your operations in the right order and distribute them among the threads it has to keep your CPU busy and your number of requests per second optimal. At some point, one of your lambda will launch a request on the network. It should then immediately return to make sure that it does not block the thread that is running it. Avoid writing blocking lambdas. If your lambda is done, then the thread has nothing more to execute. It is free to do something else. Your request has been launched, and there is a handler somewhere that will trigger a signal when the response is there. Your framework knows this handler. It knows when the data from the response is available. Then it is its job to run your next lambda, the one you define that will react on this data. This lambda is invoked once again by your framework with this data as an input. Because these 2 operations are 2 different lambdas, the framework thread can do something else in the meantime, like launching more requests or running other lambdas. There is obviously an overhead in doing that. Nothing is ever free, but it is still much cheaper and much more efficient than blocking a thread. This second solution has been thoroughly explored and optimized over the last 10 years, and this is what asynchronous frameworks are doing with great success. Using this technique, you can dramatically increase your number of requests per second, and you have many frameworks to choose from to do that. What does it require from you as a developer? Well, you need to change the way you write your code. Remember, you need to create these atomic, non-blocking lambda operations. Now I would like to take you through an example that I borrowed from Tomasz Nukiewicz, a famous author and speaker, and a renowned expert in asynchronous programming. The problem you need to solve is the following, and it's a very classical problem. A user is doing some online shopping, and what you want to do is make sure that everything is saved in a database and that you send this user an email with a receipt at the end of this transaction. The first step consists in making sure that the user is saved in your database. Then you fetch the shopping cart, and then you loop over the items that person chose to compute the total price. Pretty simple. And then you invoke the payment service and record the transaction ID. And with all these elements, you send the email with all the details of the transaction. All this is pretty easy, pretty straightforward, and the code is simple enough to understand. Actually, anybody can easily check it to make sure that the business process has been correctly implemented, because it's just a simple piece of code. If you need to debug this code for some reason, executing it step by step is easy. Writing unit tests, because you write unit tests, don't you, is also super easy. More than that, if there is a business requirement that tells you, oh, if a person spends more than 100 on our site, we would like to give that person a coupon. You know exactly what to do and where you need to add your code. And this code is going to be very simple. So in a nutshell, everything you need to do with this code is easy, because it's just a piece of simple, imperative, step-by-step code that exactly maps the business process that was specified. It's almost boring. The only problem is that, as you saw, it will not scale. And what you need to do is to adapt this code to the asynchronous framework your application is using. What would it look like to adapt this code to the CompletableFuture API? The CompletableFuture API is part of the JDK, so it's pretty easy to set that up. Well, it looks like this, and that's a problem. Do I really need to go through all the problems that this code has? The imperative version of this code was easy to follow, and thus it was easy to spot in the code if a mistake was made in implementing the business process. In this mess, how can you check that? Let me just highlight the portions of your business code in it. What you see is that they are drowned in a mess of technical code, making it super hard to understand how these pieces of code actually work together. Even the types written by these elements of business code are hard to spot, because they are not there. See, what is the return type of this call to payment service.pay? How can you check that you are returning the right thing? And now suppose that you need to implement the new business requirement we just talked about a minute ago. If a person spends more than 100 on our site, we need to give that person a coupon. Where are you going to add this code, and how can you add it in this mess? But that's not the only issue, unfortunately. Debugging such a code, for instance, running it step by step, is next to impossible. Writing unit tests is also super hard. All you can test is the process as a whole, which is not really a unit test anymore. These are the most obvious caveats, but unfortunately they are not the only ones. If something goes wrong in the imperative version of the code, the stack trace will give you the exact context in which your code is running. You know exactly where you are and what element of your application actually called you, because it's there, written in a stack trace. All the lambdas you wrote in the asynchronous version are executed by your framework, and they are executed asynchronously, which means out of the context of your business process. The element of your application that triggered this processing was just there to declare your processing pipeline, and it's now gone, doing something else. It is not waiting for any response anymore, meaning that it is not in a stack trace anymore. The real element that is running all these lambdas, getting the results and forwarding the results to the other lambdas, is your framework. So if you examine the stack trace, you do not see your application context. All you see is your framework calling your lambda. It also makes exception handling super hard. If you're lucky and an exception is thrown within your lambda code, then the stack trace will take you there and you can do something. But if one of your lambda returns a null value, for instance, that triggers a null pointer exceptions in the framework code, then you're in trouble because the stack trace does not tell you where this null value came from. Suppose one of your lambda does not return because it's waiting for a response that is not coming. If you're lucky, you have a timeout somewhere that was set up in your code. But then again, the stack trace tells you that a timeout exception was thrown with no information about what lambda actually triggered the timeout. And if no timeout handling was set up, then you have a stranded lambdas that is preventing a process from producing a result. This lambda is lost somewhere in some event queue, never to be activated again, and next to impossible to spot. Not having a meaningful stack trace has a cost. It makes your code hard to debug, and for the same reasons, impossible to profile. Asynchronous programming can give you great performances, but the cost of maintenance is actually super high. It's not an ideal solution. So if we step back to our initial problem, you know that the asynchronous approach can dramatically improve your request per second performances, which is what you need, but you also understand that it comes with a cost, which is mostly a maintenance cost. So now you are left with the first solution, which was making threads less expensive. Before we move on, we need to answer a question. Less expensive by what factor? What do we need to make it so that you could solve your CPU usage problem just with less expensive threads and not having to rely on asynchronous programming anymore? Well, the answer is in this little table we did previously. We need to be able to launch in the order of 1 million threads. What we can do currently is launch in the order of 1,000 of them. So we need a new type of thread that is 1,000 times less expensive than the current model to be able to launch 1 million of them. If this can be achieved, then writing your code in an imperative blocking way becomes compatible with the number of requests per second that you need. And you will not need to write asynchronous code anymore. Would it work if the gain is only 100 times less expensive instead of 1,000? Well, no, because in that case, your CPU usage would be only 10%. And if the gain is 500, then the CPU usage would be 50%. So to reach max throughput, you would still need to rely on asynchronous code. And this new type of thread would actually be useless. So gaining a factor of 1,000 is actually the minimal gain you want to achieve. And this is what virtual threads are giving you. Virtual threads from the JDK 21 are much lighter than platform threads by a factor of more than 1,000. You can easily launch 1 million of them, even on a small machine. Virtual threads are so lightweight that you do not need to pull them anymore. When you need one, just create it and let it die when you do not need it anymore. What is the magic trick that makes this possible? Well, when it comes to computing, there is no magic trick, just engineering, and in that case, very smart engineering. Underneath, you still have platform threads, because this is the tool operating systems are using to execute several tasks in parallel, and you cannot avoid using them. So the trick is still about running several tasks per platform thread. A virtual thread has to run on top of a platform thread because there is no other solution. And if you want to have 1,000,000 of them, it means that they need to share these platform threads. Let us first create a first virtual thread and run it. For that, let us go back to our previous example and let us make the imperative code we wrote a runnable so that we can run it in the thread we create. And then you need to create a virtual thread, which is very easy too. You now have two factory methods added to the thread class, of virtual to create virtual threads and of platform to create, well, platform threads. Of course, you can still use the old pattern that is calling new thread directly. You can then use one of the methods available on the builder you get to create exactly what you need. You can set the name, you can allow or disallow the use of thread local variables. And by the way, there is also a factory method that has been added to the executors factory class called new virtual thread per task executor. The executor service you get actually creates a virtual thread on demand every time you submit a task to it. It does not pull anything. This executor service may be very useful if you have a concurrent application, for instance, built on such an executor service, and you want to check what kind of gain virtual thread can give you. And then, because a virtual thread is a thread, you can do with it everything you can do with a regular thread. You can start it, you cannot stop it, or suspend it, or you can join it, for instance. There is one thing that you cannot do with a virtual thread, which is you cannot make it a non-daemon thread. A virtual thread is always a daemon thread, so having live virtual thread in your application will not prevent it from exiting. It also means that all the problems you may come across with platform threads are still there. Race conditions, deadlocks, visibility, tierability, all this good concurrent programming stuff is still there with virtual threads, so be aware of that. But the good news is that it also means that all the solutions that you know to ensure the correctness and the safety of your code are also the same. Now, let us take a closer look at how things are working when you are executing the code from our example. What is happening when a virtual thread is executing a runnable? Internally, there is a special pool of platform threads, which is, by the way, a modified fork join pool, that is there to run your virtual threads. So, your virtual thread is mounted on a platform thread from this pool, and your task is executed by this platform thread through your virtual thread. If you print a virtual thread, you will get this result. It shows you that your virtual thread is mounted on the worker one of the fork join pool 1. How many such platform threads do you have? Not that many actually, one for each core of your CPU. At some point in our task, the code is making a request on your database. It is calling repo.contains_user. This is a blocking code, and you know that you want to avoid blocking a platform thread. This is exactly the role of a virtual thread. Your virtual thread detects that it is actually executing a blocking I/O operation. And instead of blocking the platform thread it is running on, it unmounts itself from this platform thread, moving its own context, that is its stack, to somewhere else in a memory, namely in a heap memory. What is happening under the hood is the following. A virtual thread is actually executed by a special object called the continuation. This continuation object is in the non-public part of the API, so you should not use it in production. This continuation has a run method that executes your virtual threads, and that in turn executes your task. When a blocking call is issued in the Java NIO API, for instance, a call to continuation.yield is made, And this is the call that unmounts your virtual threads from the platform thread and copies the stack of your virtual thread to the heap memory. Of course, continuation.yield is only invoked if this blocking call is being executed in the context of a virtual thread. It works like your virtual thread was saying, hey, I won't be needing the CPU for a while because I'm waiting for a network response. So please remove me from this platform thread. And by the way, blocking calls are not found only in Java and I/O. Actually, all the blocking calls you can think of in a JDK have been refactored to call this continuation.yield. And that also includes the synchronization objects from Java util concurrent. And then at some point, the data from the response is there. The operating system handler that monitors this data then triggers a signal that calls continuation.run. And this call to run takes the stack of your virtual thread from the heap memory where it has been saved previously and puts it in a waitlist of the platform thread it was mounted on in this fork join pool. Because this is the way the fork join pool is working, if this thread is busy and another thread is available, then this other thread will steal this task from the first thread. So you may observe that your task actually jumped from one platform thread to the other while it was blocked. This is how virtual threads are working under the hood. As you can see, no magic, just very smart code actually doing wonders. What is the cost of all this, and are there any caveats? Well, there is indeed a cost, and there are indeed caveats, so let us go through them. The cost of running a task in a virtual thread is the cost of running in a platform thread plus an overhead. So it is more expensive to run a task in a virtual thread than running it in a platform thread. Let me say that again. It is more expensive to run a task in a virtual thread than running it in a platform thread. So why would you do that? Because the cost of blocking a virtual thread is tremendously lower than blocking a platform thread. What is the cost of blocking a virtual thread? Well, it's the cost of moving the stack of your virtual thread, that is several tens of kilobytes, from the stack to the heap memory and back. It's not free, nothing is ever free, but it is certainly much less expensive to block a virtual thread than to block a platform thread. That would include the probable context switching that you will have to pay. So running a task in a virtual thread is interesting only if it is a blocking task, because there you will have this gain. Running a task that is doing only in-memory computations in a virtual thread is useless. Don't do it. This is not why virtual threads have been made. Don't run your parallel streams in virtual threads. You'll actually degrade your performances. You are not doing I/O in your parallel streams, right? If you check how the JVM is working, you will see that the just-in-time compiler is still running in a platform thread, and the same goes for the garbage collectors, for instance. These are in-memory computations. They do not run in virtual threads. The caveat you need to know has to do with native code calls and synchronization. Moving this stack around is okay as long as your code is not playing with addresses on this stack. You cannot get an address on a stack in Java, but you can in C or C++. And your Java code may call some C code or some C++ code. So if the JVM detects that you have native calls in the stack of your virtual thread, it will pin this virtual thread to its platform thread to prevent it from being moved to somewhere else. And a problem you may have heard before is that the synchronized block behaves in that way too. If you have a synchronized block in your stack, then your virtual thread is pinned on your platform thread. What can you do if you are in this situation? Well, your first reflex should be to do nothing and assess your code precisely. A performance problem may occur if you pin a virtual thread on a platform thread for a long time. If your native code or your synchronized block is only doing some in-memory computations that will take in the order of the hundreds of nanoseconds to execute, then odds are that you will not see any performance loss. It's the case if your synchronized block is guarding some in-memory data structure to ensure its correctness, safety, and visibility. On the other hand, if you have some I/O operations in this synchronized block that can pin your thread for hundreds of milliseconds, then maybe it will be a good idea to do something about it. The good news is that you can replace your synchronized block with a reentrant lock that will do the same without pinning your virtual thread. But remember, you don't have to do that. There are still many situations where pinning a virtual thread on its platform thread will not affect your performances. As usual, when it comes to performances, measure, don't guess. Alright, let us wrap up all this. Virtual threads are a new kind of threads in the Java space. They are cheap to create, you can have a million of them. Cheap to block, you do not need to rely on non-blocking asynchronous code anymore. Running some blocking code in a virtual thread is just fine. Please do it. You do not need to pull them, create them on demand, and let them die at the end. This is what the JDK is doing. You should only run blocking, typically I/O code in a virtual thread. Running in-memory computations is useless. Don't do that. And remember that when you run some native code or when you do some synchronization, your virtual thread is pinned on its platform thread. That may be an issue if you are doing some I/O operations in your synchronized block. One last word, odds are that you will not work directly with virtual threads in your application, but don't worry, most of the great frameworks you know are already supporting or at least working on supporting virtual threads, and that includes Jetty, Vertex, Tomcat, Spring, Quarkus, Spring Boot, or Helidon. So yes, that's a lot. If you want to learn more about virtual threads, don't forget to check the descriptions. I just added link to other resources that you may find interesting. If you're interested to learn more about the other new features of the JDK 21, you can also check the other episodes of this series. Again, see the links in the description. And with this, I'm out of coffee. So that's it for today. Talk to you soon.